Now we know that the reaction is to push back, so that means this is the amount being pushed back by RE. And what is this? That is the change of the deformation due to RE, so that is this one. Again, right now I use blue color. Blue color corresponding is the influence of the RE onto the whole model. Influence of the RE onto the whole model with respect to this the first segment, that is this one, right? Yes? And for this one, the blue is moving leftward. Let me give the direction. And this one is moving rightward, right? So simply the net displacement is, from here we can tell simply is a competition between the two numbers. Right. So for example, let me put a sign convention, say the sign convention moving rightward is positive, say moving leftward is negative. So simply our answer is the two terms, that term minus this term, right? Okay, so for that case will be equal to 83.16 times 10 to the minus 6 meter, and that is moving rightward. Are we okay? So again, here I decompose the problem solution into two subsystems. One subsystem is like this. For this case, we calculate the displacement is assuming that it would have no constraint. Then that is represented by the red color. And then the second subsystem is due to the influence of the reaction that given produced at the ground here, at the constraint here, and that push back to the model, and that is a little bit described by the blue, and which is this one for the first segment. Okay. Right now I'm waiting for Blackboard OIT to help me to increase the space, the quota space for our Blackboard ES331. And right now I'm asking a really nice lady to help me record the lectures. So once the space has been augmented on Blackboard, I'm going to upload the lecture notes, in video clips. Okay, hopefully that can help. You to review. But otherwise, right now, because the space is so limited, even 1 gigabyte of the video clip is not allowed because the space is so limited. If before that happens, if you really want something, you come by my office. I have kind of backup offline. I can provide that to you. So that is for these examples here.
Can you clarify why the relationship is B to A and then C to B?
Yes.
I feel like C to A.
Yeah, so let me redraw this one again. So this is C, this is B, this is A. So the displacement of this one is basically delta C equal to delta C relative to B plus delta B relative to A and plus A. And because A is fixed, so this is 0.
Okay.
Okay? Yes?
Do you know when the SI schedule thing will be posted? The SI schedule?
SI schedule?
Yeah, for the supplemental instruction thing.
Oh, has he sent the?
Yeah, he did the survey thing. He put it on there.
So he got a survey on already.
But I think
I thought he said a few
only 10
days.
people that answered so far.
Huh?
When I looked last night, there were only like 10 people that had gone on and actually put in the
Only 10 people
Yeah.
responded. So maybe that'd be helpful if everyone can respond to that kind of survey, and the survey is on Blackboard. Otherwise, I think if you want to respond it by, I think I will try to get the tutors to fix the schedule on Monday at latest. So if you wouldn't respond, then we just, based upon whatever we surveyed, and we fix the schedule. If that schedule didn't fit to you, sorry, because you didn't respond. Okay? So hopefully you can respond, and then right away, hopefully Monday we should have the information, we can post it. Thank you. And this question is a challenging question, and actually embeds a lot of the concepts. So I use this as the model examples, hopefully can help you. So with these things, I will keep certain calculations because I'm going to use the same examples for the next section we call the thermal strength. And let me erase the certain portions. So let me keep this one for this moment and let me go down here. This is a new section we call the thermal strength. The thermal strength is this. If we consider a material and say this material has Young's modulus E, this material, assuming that is uniform, that means has a uniform cross-sectional area A, and the length, let me call that L. And this material right now, before this section, is we always to apply a certain load, axial loading, to deform this material. In addition to the real axial loadings in solid mechanics, we have a different loading type we call the thermal loading. Thermal loading basically is the change in the ambient temperature and to extend or to shrink the material. If the temperature gets rise, delta T equal to greater than equal to 0, then this will be expanded due to thermal expansion. If delta T is negative, then basically this material is going to shrink. Okay, and corresponding to these properties, I need to introduce additional term, alpha. And here the alpha is called the coefficient of thermal expansion. And sometimes we call using the CTE. Take the first letters of the term CTE. And alpha usually is in terms of the unit is in the unit of, for example, 10 to the minus 6 per, for example, Celsius, or 10 to the minus 6 per Fahrenheit. And for example, for copper, the alpha, this material, and alpha, for copper, that is 18 times 10 to the minus 16 per Celsius. And for silicon just like sand or glass, and this is about 2.8, 10 to the minus 6 per Celsius. And for others, for steel, I forgot, because why I remember the two materials, because that is part of the common material used in your cell phone or your iPad. And they use a lot of this kind of two materials, so I remember the two numbers. You can see, because for that kind of the cell phone, I say that in the single black chip, there's a very tiny, very thin, but there's a lot of the components there. Those components are made of the two, basically made of the two materials. And then what happened? If this would be the silicon, if this would be, say, copper, they kind of grew together in concept. You can see that is a huge thermal difference, right? So once the temperature, for example, if you use it and the temperature heated up, you feel warm on your cell phone. Then basically once the temperature heated up, copper try to expand more, much more than silicon. So basically, these both things will become like this. Right? And once temperature cooling down, and then basically this will curve down. Once you are using your cell phone, say playing, texting, or playing the games, and basically the temperature of operation basically is up and down, up and down. That is, you simply is kind of let me put it this way, you kind of risk your expensive electronic device is into this way. Certain key component into this. If you imagine that would be the wire, what happens? A few times later, they're going to break. You know what I mean? Okay. But of course, right now the current the semiconductor industry and the electronic packaging industry, they won't put the device so vulnerable to this kind of operations. But they have a kind of default design, the time to failure. They should have the very good the time for if you operate normally, okay, that should be fine. But in concept, the thermal loading will have this kind of effect. So before we proceed to go this, we give certain basic definitions. Thermal strain or the thermal expansion is this. We define by the CTE, the CTE multiplied with delta T. This one will give us the thermal strain. Thermal. And usually we use the epsilon T, the subtract T, to indicate the thermal strain. Okay, the T indicate the thermal strain, and that is a common word we've been used. So in this way, we can calculate the corresponding thermal deformation. The deformation due to thermal simply is equal to the thermal strain times the original length. So that is the original length. So the longer the length, the material, the larger the deformation. That is a basic concept, and then we can utilize this concept for doing something. So for the same examples, how about let me redo this one, let you follow me. Right now we don't have loading. We only have the thermal loading, so we don't have the external loading. So right now for this case, and again the same setup, we have the constraint here. And for this case, the same geometry, the same length, the same province. And here we are given delta T. And for this exercise, we are given delta T equal to 80 degrees. So that means we try to increase the ambient temperature with respect to the original of the material. And then we have the alpha. For example, alpha in the portion AC will be equal to 11.7 times 10 to the minus 6. And alpha in CE will be equal to 20.9. Again, for the same questions, we want to calculate the two informations here. So the solution is similar to this. The first one, due to these thermal loadings, we should be able to calculate what is the deformation in AC? Deformation in AC in this segment, simply we pick up that formula, that is alpha times delta t times the length of the AC. So for this case, it's 11.7 times 80 times 0.3 meter. And if you work out these units carefully, let me work out the units here for the first time. Okay, so that is per Celsius, multiply 80 Celsius, and multiply length is 0.3 meter. So from here you can see this one basically cancel it. So the unit is in terms of the meters or whatever the length unit you use. So for this case, that would be, let me leave it, okay. ACE, the same thing, alpha CE times delta T times LCE. So this one will have 20.9 times 10 to the 6 and 80 times 0.2 meter. So therefore, from here you can see delta E basically is delta, the displacement at E, basically the two information, delta AC plus delta C, right? So the two numbers were added up, that would be 1.15 times 10 to the minus 4 meter. And what is gap? The gap is 0.12 millimeter. So this is larger than the gap. The gap is 1.2 times 10 to the 4th meter. Right? So under this situation, what happened? This calculation, assuming that it has no constraint on this side, so due to the thermal loading, that temperature is too high, and such that this end will not only touch the wall, but also begin to press. So the similar situations like we did in the earlier examples, but for this case is the material be loaded up by temperature to push the wall, compared to the previous one that is loaded up by two external loading to push the wall. But the thinking process is the same. Right? So now we can do this one. So now again, let me using the same blocks here and using the two color code. And for example, this is the original. Let me draw it. So this is AC. This is the original shape. And let me use the red color to indicate if the virtual displacement due to thermal loading. And so due to thermal loading, this material will be expanded by that much for this segment. The second segment will be expanded by that much. And here, that is the wall here. That is the wall here. And then here we can see that will exist a reaction force. So basically, right now, this is our calculation. Let me label it. So this is 6.15. So that means here, let me give this. This is 0.12 times 10 to the minus 4. And from here to here. From here to here, that is our calculations, is 6.15 times 10 to the minus 4 meter, right? Okay, that is what we done in our calculations. And then you can see that due to the existence of the wall, they should exist a reaction. They will produce a reaction force, that we call RE. Again, RE is to push back such virtual deformed model. In this way, we'll maintain this end here. And that model will be something like this.